All right, so we're at 6:30. Jeremy, you want to go ahead with announcements?
All right, sure. So SouthEast LinuxFest, it's just around the corner, June 8th through 10th. Registration just went live. The schedule, I'm going to put it up here shortly. Basically, before the meeting's even over, all the logged emails lists are going to have my email in them.
Jeremy,
yes?
I want to see your eyes.
I have a Sidekick laptop, and that's what the meeting's on. That's why I keep looking that way. So also, let me pull up some of the items here. So this is our 10th anniversary for Self. So there's some special things that are only going to occur this year as part of that. All this for supporting attendees, we're going to have a really good custom color lanyard. I've commissioned an artist who's doing some work on that. So stay tuned on that. Everybody's always wanted Self stickers. We're going to have a nice 8.5 by 11 sticker meal sheet with tons of custom stickers on it. And what I'm calling the Book of Knowledge, it's a binder that's meant to be in easel form. So it's self-supporting and stands up into its own A-frame. And inside of that, we're going to have a bunch of custom self-branded cheat sheets for programming languages, markups, editors, distros, all kinds of good stuff. And new for this year, for those who can't make it to Self, we're going to have a remote attendee option. $5, you get all of the talks streamed live or with minimal delay. And then, as usual, after a couple months, it'll just be public on YouTube. But for those who want it immediately, just a $5 option, and we'll hook you up. Zach has overhauled our AV production. So, in fact, it may even be headless. We might literally this year have room moderators who go in, start the talk, and then leave because it's all going to be remote into the command room this year. You'll want to definitely check the schedule. There's some speakers on there whose names you may be familiar with, maybe not. To say nothing of Jace, who's also in this call and also speaking. Geeks with Guns is going to be bananas. We've doubled the number of lanes we're going to do this year. We're bringing in like a half dozen specialty pieces of equipment. And by the way, you get more than 100 rounds if you do it this year. Like, we're giving you ammo as part of it. Just go to the website. There's tons and tons and tons of info I just put up, southeastlinuxfest.org. Registration is live. Go do it. Hope to see you there. And if you can't make it, remote attendee.
Awesome. All right. Thank you, Jeremy.
And Ben, Ben, you're also going to have a booth there that's representing Cola Lug and Upstate Lug. Ben?
Oh, this is the first I've heard of it.
Oh, I thought you said you were going to. Oh, maybe I misunderstood. Okay.
Hold on. Let me hold an impromptu meeting. We've decided there's booth space for you. Yeah, there's booth space for you.
All right. All right. You got me back on that one. Thank you. All right. So with that, well, I might be able to work out something with Jeremy. We'll see. Jim Salter has just arrived, ladies and gentlemen. Okay. All right. So we're about ready to start. I'm Ben Francis, and I'm so happy to have Howard Chu with us today from Simus Corporation. Howard was one of the original developers of OpenLDAP since 1999, and he played around with. Well, I mean, he was a major contributor to OpenLDAP for many years. I think we got. They reached the limits of the Berkeley database that was the back end for OpenLDAP. So he set about in 2011 to invent a better, faster database. And not only did he do a better, faster database, but he did it 100 times better, which is just about unbelievable as since at that point, we had been having databases for 40 years. So without further ado, Howard, if you could take it away, we would be so happy.
Sure, thanks. So sorry, I have to turn my camera off because it's just lagging everything else, but all the good stuff's on the slides anyways. So I hope you guys can follow along. If you're not familiar with OpenLDAP, it's an open source project that's been around since 1998. It started actually out of the University of Michigan LDAP code, and I've actually been working on it since about 1998. Simus Corporation, my company, it was founded in the spring of '99. We were all a bunch of refugees from a large enterprise software company. So along with being a founder of Simus, I've been writing open source software since the early 1980s. I've worked on all of the GNU developer tools, GCC, GNU Make, GDB, the linker, everything in the developer tool chain. I've worked on lots of other projects. Back in the early 1990s, I worked for JPL. I wrote software for the space shuttle. I actually do have software still in orbit today, has never crashed. All right, so topics for this talk about the Lightning database, background of where it came from, some of the cool features that are built into it, the approach that got us to where we are, and then a kind of a deep dive into the internals of how it works. And then, as someone was talking about some graph porn, we'll look at some of the results, benchmark testing. Okay, so LMDB is very similar to Berkeley DB in the software design.
Hey, Howard, I don't think your slides are advancing. Oh, there we go. Okay.
Yeah, I noticed that. Yeah, the slides are lagging a bit, aren't they?
Yeah, okay.
Yeah. It even still hasn't caught up here for me, but we'll see how that goes. Are you guys looking at the background slide right now?
We are indeed.
Okay, good enough. All right, so the API is inspired by Berkeley DB because, in OpenLDAP, we've been using Berkeley DB for a long time, used it very heavily, used a lot of its more arcane features. So we've been deep inside the Berkeley DB code for a long time. But at the same time, we found that there's a lot of parts of Berkeley DB that we never actually used in OpenLDAP, or we tried to use them in OpenLDAP and found that they didn't perform very well, such as their use of extensible hash tables. And also, we tried to get away from the things that have caused us continual problems in the course of deployment of OpenLDAP. So in Berkeley DB, it's fairly complicated to tune the caches properly. The lock system is super complicated. Administration of transaction logs is always difficult. It takes a lot of, active involvement, and crash recovery wasn't always a sure thing. So these were problems that we really wanted to try and get away from. So in LMDB, first of all, it is a key value store like Berkeley DB. It uses B+ trees, also like Berkeley DB. It's fully transactional, it's fully ACID compliant, and again, same as Berkeley DB. It uses multi-version concurrency control, and readers in this system never block. Right? Nothing ever stops a read from succeeding. So that's a little bit different from Berkeley DB. Berkeley DB supports MVCC, but it doesn't actually have wait-free reads. All of the database is stored in a single file, which is memory mapped, and the memory map is the only access mechanism to the data. So there's no separate caching, so there's no cache configuration needed, and there's no cache tuning. The method of writing to the database is completely crash proof. Right? It's guaranteed that we can never corrupt any in-process or in-use data structures. which means no matter what you're doing, if you pull the plug on the machine, the next time you power up, the database is immediately ready to use. The code is extremely optimized and extremely compact. A typical x86 or x86 64 build compiles into about 50 or 60 kilobytes of code these days, but it still fits entirely in a CPU's level 1 instruction cache, which means it can run with pretty much zero wait states as far as instruction fetches. And it runs on just about every modern OS out there. Okay. Are you guys looking at the concurrency support here?
Yes, we are.
Okay, good. Because again, the slides on my side are not catching up with me. Okay, so the library supports accesses both from multiple processes and multiple threads concurrently. And so this is kind of a unique feature. I mean, Berkeley DB supports it, but a lot of other embedded databases are single process only. So this is, again, a distinguishing feature. The concurrency model is a single writer plus an arbitrary number of readers. The writers never block readers, and the readers never block writers. And since reads don't actually take any locks, the reads scale perfectly linearly across all available CPUs in the system. Every transaction is fully isolated with MVCC. And so if you're familiar with SQL or relational database jargon, this is the highest level of isolation. It's called serializable isolation. Transactions can actually be nested within each other. So this is a feature that a lot of SQL databases tend to use. And it also supports batched writes, where you can throw a bunch of write operations into a single batch and commit them all at once. That saves a little bit of disk I/O overhead. So the next slide is the technique that we use to actually write the data is called copy on write, which means you never actually modify live data, right? You never touch live data. And since you never touch live data, that means none of the database structure can be corrupted by incomplete operations, system crashes, power failures, whatever. And because of this, we don't need write-ahead logs, we don't need transaction logs, and we don't need to maintain them. And we need no special recovery procedure after a system crash. As soon as the system boots up, the database works.
Hey, Howard, we haven't advanced to that slide yet. We're still on concurrency support.
Oh, okay. All right.
And we got a little message saying you're having connectivity issues.
Oh, well, why does that not surprise me?
You're on the features uses copy on write?
Yes.
Okay.
Is that where you are now?
That's where I see.
Really?
Okay.
We're still on features concurrency support.
Interesting.
Yeah,
wow.
It just updated to copy on write about 5 seconds ago for me.
Okay.
We're still lagging.
Still lagging. All right. Some of you are getting it and some of you aren't. That's even better. All right.
Okay, all right. So we got it on another computer. So go ahead. Thank you.
Okay. So we'll go to the next one. Next, let me know when you see single level store.
You got single level store?
I can see it.
All right.
Okay. All right. So the rest of you are just going to have to imagine. All right. So the basic concept for a single level store, all read operations are satisfied directly from the memory map. So since the entire database is accessed through mapped memory, and we just give you a pointer directly to that memory, we don't have to make any copies of the data before returning it to the user. Okay. So that's the default operation. Also, normally we do make copies for writes, but there's an optional mode where you can also do writes directly into the memory map. And so in that case, if you use that option, then writes are also direct and single level. And you might think that just using direct accesses to data is going to be slow, but in fact, the operating system and file system are already caching all of these accesses. In Berkeley DB, there were a bunch of other caches that you had to configure, but for the most part, they are a waste of memory because the operating system was always caching that data anyway. Right? So we eliminated that, so there's no wasted memory in application level caching. Everything is cached by the OS.
Is that in every OS?
That's true in every OS, yes. The OS is always caching your data accesses. Now, this last point here is kind of an obscure feature. You can actually store, if you're doing, complex data structures or objects, you can actually store them directly into the database, even with their pointers intact, instead of needing to serialize them into a format like, JSON or XML or whatever else. And the way this works is you create the memory map and you tell the OS you want the memory map to be at a constant address. All right. So normally when you memory map a file, every time you open the file and start the memory map, the OS can pick a different address for it. Okay. But if you tell the OS you want it to be at a fixed address, then it'll always be there every time you use it. And so any pointers that you use that are based on that address will always be valid. And once you know that your pointers are always valid, then you can just stuff them in there without doing any kind of serializing and no deserializing, no marshalling, no unmarshalling. Okay, next slide. One of the things we really aimed for was to simplify the experience in OpenLDAP, and also just as an application developer. Are you guys seeing LMDB config slide?
Yep.
Okay.
Yes.
It hasn't updated for me here, but okay. So just as an example, in OpenLDAP slapd, to configure an LMDB backend, you just need to tell it, where in the file system do you want it and how big do you want to let it grow, right? The maximum size. Whereas in Berkeley DB, all right, you have to tell it where it's going to store it, but then you have to configure at least 3 different caches. You have to configure buffers for the transaction logs, and you have to configure how many locks and lockers and all these other things that you're going to allow the system to use. So there's quite a lot more to think about, and it takes a lot of balancing to make all of these parameters work well together. So in LMDB, none of that is an issue. You just say, give me the database, don't let it grow bigger than this size, and don't worry about it. So we talked a little bit about the difference in performance compared to other existing databases. And this slide, we're looking at read performance. The graph on the left is performance for sequential reads, and the graph on the right is for random reads. And this is with small records, so they have 16-byte keys and 100-byte values. And some of the databases being compared to, you see SQLite 3 there. The TreeDB there is from Kyoto Cabinet project. LevelDB there is the database from Google. We have Berkeley DB there and LMDB. And so you can see on the sequential reads, LMDB is doing like 14 million reads per second. And the closest competitor there is LevelDB at just over 4 million per second. And on the random reads, the scale is, the magnitude is a little bit smaller. We're only doing 700,000 or 800,000 reads per second. But again, compared to all of the other databases, it's much faster. And then, next slide. If we change to the same test, but using large records, these records are 4,000 bytes in size. Is that right? No, these records are 100,000 bytes in size. And the test on the left is sequential, and the results on the right is random access. So are you seeing this slide with 33 million reads per second for LMDB?
Yes, we are.
Okay. And so, yeah, you can see that basically all of the other database engines on this test are just down in the noise. I mean, they barely register at all. So this is just to give you an idea of the magnitude of performance difference you get from switching into using LMDB. All right. And then the next slide is the same data, but plotted on a logarithmic scale, just so you can see that the other databases did something instead of just being flat lines there. But yeah, we are talking multiple orders of magnitude difference in performance here.
Ooh.
All right. Now, over the course of the past few years, we've tested this thing extensively on all kinds of systems. You know, every file system that we could find which is supported on Linux has been tested. We've tested on, you know, old hard drives, SSDs, NVMe devices, you know, anything we can get our hands on, we've tested. Now, LMDB itself doesn't make very much use of malloc, but a lot of these other database libraries do. So we've tested with multiple different malloc libraries. We've tested with different compression libraries, you know, different server configs, different small to large virtual machines, small to large physical servers, from 32 gigabytes of RAM up to a terabyte of RAM, machines with up to 64 CPU cores. Actually, okay, so you were asking me about things that have changed from 2015 to today. I can tell you that last year we tested at Oracle headquarters, and they gave us a machine with 2048 CPUs to test on. So we've definitely been all over the range of large scale, vertical scale machines. And you know, different usage scenarios from small in memory to databases that are multiple times larger than the size of RAM. One of the things I'm pretty happy about is, you know, we make some claims that LMDB is crash proof, right? And that is by the nature of the design and the copy on write approach. And back in 2014, two different research teams actually studied crash behavior of LMDB and a number of other database engines. And they did indeed verify that they could not corrupt LMDB with any of their test tools. So it has been tested both, you know, academically and in the field industrially. You guys are seeing the crash proof slide?
We are.
Okay, moving on to the next. So talking about the design approach and what were the problems we were trying to deal with, and what were the solutions that we chose to get there. All right, motivation. So in OpenLDAP SLAPD, the Berkeley DB backend always required careful tuning. First of all, there are 3 different layers of caches in that backend, and each layer treats data in a different format. You know, so the raw on disk format that Berkeley DB uses is different from the format that that SLAPD needs, and you know, each cache layer is in a different format. So a particular item of data actually has a different size depending on which cache layer it's living in. And you're fighting to balance each of these 3, all right? So the OS is caching things, the database library is caching things, and SLAPD itself is caching things. And the fact that Data can appear in each of those three places, or it can appear in all three of those places at once. It makes tuning a real nightmare. And you can't just say, oh, this is too many caches, let's turn one of them off. You can't actually turn off the OS cache. It's not possible, right? If you try and turn off like the database cache or the slapd cache, you find that performance just plummets. So it's like we have a necessary evil here, but it's getting really awkward. The other thing we found is that the actual code used to maintain the cache was probably the most complex part of the backend. All right. We use two different sets of locks. Berkeley DB has its own lock manager, and then we had to impose another level of locks of our own on our own cache because the Berkeley DB layer was too slow. And the other thing about it was that even in routine operation, if you get a couple of different requests coming in to write to different records at the same time, deadlocks happened all the time. And that was just normal. Deadlocks were not a sign of an error or a logic failure. It was simply the fact that it was always possible to deadlock in standard operation. And once you hit a deadlock, one of your tasks had to give up, back off, and retry later. And so that really killed throughput for us. The other thing we found, all right, so I'm talking now, this is slide number 20, if you're getting the slide numbers on your display. I don't know.
Yeah, we're getting them.
Okay. So the caches didn't always help, and a lot of times they actually hurt. Since the data could actually exist in three places at once, it meant that a lot of memory was actually being wasted. The other thing that really killed it was, for example, if you did a search that touched a large number of records in the database, if the result set was larger than the cache size, then it would basically cycle through the entire cache, 100% of it, and 0% of the cache entries would ever be reused. So that rendered it completely 0% hit rate, which was awful. And the other thing was, when we add and remove entries in the cache, we have to malloc a memory block for them to add, and we free it when we remove them. And it turns out if you use malloc and free very heavily, as we were doing, you get into these really bad heap fragmentation situations. And in particular, glibc malloc was really horrible about this. And so you might wind up with an active data set of only 1 or 2 gigabytes, but because the heap was fragmented, your process size had grown to like 20 or 30 gigabytes over the course of time. And the heap was fragmented and wasn't able to be consolidated again. So that was, again, pretty horrible. So we looked at all these problems, slide 21, and said, you know what, this whole thing, managing the cache, it's a huge hassle. Let's just not do it anymore. And so that's the first concept is, look, the file system already caches data. It's doing it and you can't avoid it. Let's just let it do that and not duplicate its effort. And the second main conclusion was, locks are a huge hassle. Let's not do that either. So we look into doing multi-version concurrency control, and that makes it possible to perform read operations with absolutely 0 locks. All right, so that's it for slide 21, 22. The interesting thing about these conclusions was that Berkeley DB already supported MVCC, and that should have been good enough, but we actually tried to put it to use, and it turned out that it still required our own cache layer and our own lock layer, simply because even with MVCC, Berkeley itself was still too slow. And so looking through all of this, you know, we'd spent a lot of time looking in the Berkeley code, seeing, you know, how can we improve this? How can we tweak this? Whatever. And the final conclusion was the Berkeley code base is just so far down the path that it's gone that we really can't modify it to suit what we want. So we just had to abandon it. And once we made that decision to abandon Berkeley, we started looking around to see, is there anything else out there that actually does what we want to do? And the answer was no. So back in 2011, on one fine weekend in May, actually, I sat down and just started writing my own database. So that was the birth of LMDB. And ever since then, Berkeley has been deprecated in OpenLDAP. And there's a longer story that goes with that. You know, Berkeley was deprecated mainly for these technical reasons, which I've just outlined, but that got even more fuel when Oracle changed the license on Berkeley DB 6.0. They changed from the SleepyCat license to the Affero GPL license, and basically made it unusable for OpenLDAP and a lot of other network-facing projects. So that's some of the other background for you as far as the change in direction here. Okay, slide number 23. Are you all with me?
We're with you.
Okay. So the concept single level store, it's really an old idea. It's been around for multiple decades. Now, my first encounter with it was in the Multics operating system, which was written in 1964. But it actually goes back even earlier than that to an IBM project called Atlas. But the main idea is you treat all file system data as if it's simply memory addresses. And in this way, you know, we memory map an entire file into a process's address space. And so every piece of data that we want to access in the database is just another memory address. We just give you a pointer directly to that address, and there's nothing else between you and the data. Slide 24. There are some issues with this concept, right? It only works if your process address space is much larger than the size of the database you want to work with, all right? So in the days of 32-bit processors, the practical limit for your data size was 2 gigabytes. Now, back when I first encountered this concept of single level store, that was in the mid-1980s on the Apollo domain operating system. And in those days, a 5 megabyte hard drive was a big deal. So it was practical then to have a 32-bit processor that memory mapped all of the storage you could plug into it, because that was going to be only on the order of a couple hundred megabytes. But obviously, as time progressed and data volumes increased and hard drive sizes increased, it became less and less viable for a 32-bit machine. Today, you know, now that we have 64-bit CPUs pretty much everywhere, the picture has changed again. Although we don't really have true 64-bit addressing. You know, the CPUs that you can get today actually only have 48-bit address spaces. So that gives us a practical limit of 128 terabytes. But assuming you had a CPU with a full 64-bit address space, then that would give us a limit of 8 exabytes for the total database size. I don't think we're going to be running into either of these limits anytime soon, but you never know. Slide 25, design approach. So when you create a memory map of a region, you have an option of setting permissions on it. You can make it read-only or read-write. And in LMDB, by default, we use a read-only memory map. And the point of this is to protect the database structure itself from random corruptions. Like if you have a bug in your code and you start writing off into random addresses in memory, we don't want those random address writes to suddenly get persisted into the disk because we won't know about them, and the database structure will be corrupted, and we'd have no way to recover from that. So we use a read-only map, and that means any attempt that you make to write into the map immediately causes segmentation violation, which will crash your program and let you know unambiguously, hey, you've got a bug here and you need to fix something. That's one of the concepts you probably hear in programming circles these days. It's just called fail fast, right? And you want your errors to be obvious. So there's nothing more obvious than getting a segmentation fault.
So I have a question.
Yeah.
If the memory map is read-only, how do you populate it?
Okay, well, we'll get to that in a moment.
Okay,
but,
thank you.
So now, as an option, you can make the memory map read-write. And in some cases, there's a performance benefit for doing that. But, you shouldn't go into production with this unless you know that your code has already been successfully tested with a read-only map. Okay, so the slide 26 is a quote from my friend Keith, who is one of the primary authors of Berkeley DB. The main thing I like about this quote, he talks about why Berkeley DB never used a memory map as its primary interface. And mainly it's because they were using a traditional transaction log file. But I like this quote because the end is, if you crash at that point, it's all over but the screaming. Basically, if something goes wrong in a system like this, you have no chance of recovering from it. But instead, all right, so we don't want the memory map to be writable. We actually use a regular write system call to write to the file. And okay, I don't actually, all right, we'll go back to that. So here we are on slide 27. We avoid corruption simply by making sure that we never overwrite a page that's actively being used. And since we can guarantee that fact, that means the database structure is always intact, which means we don't need write-ahead transaction logs or undo redo logs, which pretty much every other database system uses. If you're familiar with SQLite or MySQL or Postgres or Oracle DB, they all use undo redo logs. We don't want that. Readers always see a consistent snapshot of the database, and they're fully isolated from writers. No data that is in use can ever be modified out from under you. So that means the readers can do anything they want to access the data, and they don't need to lock anything. They don't need to do collision checks or anything of the sort. Okay, slide 28. Now, if you look in the literature about MVCC, you'll find that a full implementation of that can be extremely resource hungry because basically they store multiple versions and they store every version from the beginning of time, right? Which means the size of your database grows extremely fast, and it grows without bound unless you do something about pruning it or garbage collecting or something. The problem with having a pruning pass or a garbage collection pass is that it actually requires more CPU and IO resources than your normal application workload, right? Because it has to scan so much of the data to actually find the garbage that it can remove. And the result of this is either you have to have a server that's heavily over provisioned, like a server that has CPU and IO bandwidth twice as great as your actual application workload, or you have to throttle your application while your pruning is running. So in either case, it's a bad outcome. Either one, you're paying for twice as much hardware as you really ought to be paying for, or two, you're slowing down your users. The other thing about garbage collection or pruning is that it requires you to keep track of the in-use status of every piece of data, and that usually means you have reference counters and locks and all these other things, which we just decided we wanted to get away from. So slide 29. In LMDB, we don't really do full MVCC. We only maintain 2 versions of the data instead of multiple versions. And this was a decision that made sense for OpenLDAP because basically, we don't care about the historical versions of the data. We only care about the most recent version of the data. So by maintaining only 2 versions, we guarantee that the data size doesn't keep growing at a ridiculously fast pace. And in LMDB, we maintain a free list that tracks the IDs of unused pages. So once we've copied a page to modify it for a new operation, then the original page can be marked as free. And then the original page gets reused for new write operations down the line. And so since we can do all of this free list tracking, we can do a lot of the write volumes without heavily increasing the size of the database. And all of this tracking in LMDB is done without the use of any locks. Okay, so slide number 30. This is just an interesting footnote. The B-tree code that I use in LMDB actually came from code that was written by Martin Hedenfalk in the OpenBSD project. And it was actually for LDAPD, which is another open source LDAP server. So we took that code, stripped out a whole bunch of pieces that we didn't want, threw in a couple of pieces that were in slapd that were useful, and changed from his append-only design to the LMDB page reclaiming design. We also added a bunch of new structures to it to give us some features that Berkeley DB provided that we still wanted to have. Slide number 31. So the result of that first piece of work was a library that was under 32 kilobytes of code and compares to Berkeley DB at 1.5 megabytes. So you can see that we've really stripped out quite a lot. But we still try to keep it similar to Berkeley DB just to make it easier for us to port the OpenLDAP back BDB code over to use it. Slide number 32. Are we all there on 32?
Yep.
Okay. So just as a, just as an idea of the scale of footprint we're talking about, this is the size of these programs, a benchmark program, where the main program of the benchmark is identical, and then it's just been written and linked against different database libraries for test purposes. So the original DB bench at the top is from Google's Level DB. And then the next one down is Basho Level DB, and then there's Berkeley DB, Hyper Level DB, and then LMDB, RocksDB, TokiTech, TokiDB, and Wired Tiger. And the point to get out of this is just, is you look at the MDB benchmark program, it's, at 7,900 lines of code, it's certainly the smallest in source. And if you look at the size of the text and data, it's the smallest object file too. So it's possible to run LMDB in a machine with as little as 256 kilobytes of RAM. If you really,
I'm sorry. What is MDB?
which is what?
What is MDB?
Well, MDB was actually the original name of LMDB. And down the line, we changed it because it turns out that MDB is also a well-known file extension for Microsoft Access databases. And I really didn't want to be confused with that.
No, you don't.
Yeah. And there were at least 2 or 3 other projects that used MDB as their acronym. So we had to get away from that. Okay, so slide number 33, we're looking at internals. So here, I'm going to walk you through a little bit of how other typical databases operate, and then I'll show you the difference to how LMDB operates. On slide 34, we're just looking at a couple building block pieces for the next illustration. So for example, you have a database that uses transaction logs. Okay, this would be Berkeley DB or MySQL, Postgres, the majority of them, right? So you have a root page for the data, and you have on the other side a log file. And when you want to perform a write operation on it, slide 36, the first thing you do is you describe the write operation in the log file. And then slide 37, then you actually perform the operation in the data file. And then once all of the data file pages have been written, you note in the log file that you've committed all the changes. So that's slide number 38. And this goes on. If you're going to do another operation, you first write it in the log file, 39. Then you start modifying the data file. And then finally, you note that you've committed that in the log file. That's slide number 41. Did we all get to 41?
Yes.
Okay. And sometimes, even though you've committed the data, it's still cached in memory. And so you have to do what's called a checkpoint that actually flushes all the data from memory to disk for sure. And then, so even though the commit has succeeded, it's not really permanent until you've done the checkpoint. Okay, so that's pretty much every traditional database that's out there. The first thing they do is write into the log file, and then they do whatever they wanted to do to their data file, and then they move on. Now, in the case of an append-only database, that means you're always working on copies of the original data. And in this case, for a B tree, you always have to write your updates starting from the bottom of the tree and work upwards towards the root of the tree. And every branch that you touch, or every node that you touch from the bottom to the root also has to be modified. Of course, any node that's not on that path from the leaf to the root can be left alone. And you always modify the root node very last. So here on slide 44, a very simple B tree. The first thing we want to do is make a copy of a node so that we can start writing to it. Then we create a new root node that points to it. Now, the old root and the old leaf are still there. In a multi-version database, you can still get back to the previous versions of the data. So the old root and the old leaf remain as the previous version. And if you want to keep updating, you make new copies of the leaf pages and create new root nodes. So there we are at slide 51. 4 root nodes, 3 modified leaf pages. Okay, slide 52. So in the append-only tree, we always append pages sequentially to the file. And in this case, in a copy on write database, there is a lot of overhead for making copies of every page, but the actual I/O operations are pretty fast because you're only appending sequentially to a file. So all your I/O is linear. And also, at the end of what you've written, the root node is always the last page of the file, unless you had a system crash. So that means when you're starting up from a cold start, it's fairly easy to get the database back in a working order. You just start at the very last page of the file and seek forwards to the head of the file and look for the last valid root page that you've written. Now in flat pages, this is kind of what it looks like on slide 53. We start with a root page. We write a data page. And if we want to commit the data page, then we have to write a new root page. On slide 56, we write new data. On 57, we write a new root page. And as you can see, the old pages, they're still there, but nobody is actually looking at them anymore. And going on, slide 58, another modification, and another root page. That's slide 59. And so each time the tree is always valid, but you probably aren't doing anything with the old pages. The problem with the append-only design, I mean, it's very secure, it's very robust and corruption resistant, but it's extremely inefficient in space usage. Within a dozen operations, 99% of the space in your database will be old versions of data that nobody's interested in. And if you decide to attack this problem by doing reclaims or garbage collection, you run into all the problems I talked about before, about resource requirements and throttling. Okay, so in LMDB, it's still copy on write, but instead of having a root node that just gets appended to the end of the file, there's only two root nodes in the file. They're page 0 and page 1 of the file. They're used in double buffer, like a ping pong back and forth. And startup for one of these is even faster than with append only because you don't have to search to find the last valid root node. It's always either page 0 or page 1. It's easy to tell which is which. To start up, the app just reads both pages and uses the one with the greater transaction ID. And so in this case, there's only ever 2 outstanding versions of the data, and it's not fully multi-version, but we don't really need all the other versions. Okay, so slide 64, basically showing you how LMDB operates with the 2 root pages. We create a new data node by copying the green data node, and then we set a transaction stamp on the new root node, create another new data node, and set a new root node with a higher transaction stamp. So after this point on slide 68, the old blue page doesn't have any root nodes pointing to it anymore. So since nothing else references it anymore, it is free to be reclaimed. Likewise, okay, we do another new data node, the orange page, and a new root node. And so on slide 70, after this step, the old yellow page doesn't have anything pointing to it anymore, so it can be reclaimed as well. Now that diagram is obviously highly simplified. In reality, LMDB maintains 2 separate B trees per root node. One stores the user data, which was just illustrated above. The other one stores the free list of IDs of pages that were freed in a given transaction. And we always try to reuse old freed pages before we allocate new pages from the operating system. So the database file size doesn't grow without bound. Okay, so slide 72, this is how it really looks like on disk. We have the initial 2 pages, they're both marked empty. We create some data, we commit and update one of the root pages and say, okay, we're now at transaction ID 1. Write a new data page. Now we also talk about the free list, and then write a new root page on transaction ID 2, and so on. New data page, new free list, new meta page. At this point, we're reusing an old data page for the next piece of data. And we need a new page for the next piece, and then a new meta page, new transaction ID. Okay, so there are some exceptions to this. If a read transaction is already open on a particular version of the database, that version and every version after it are excluded from page reclaiming. That means it's a really bad idea to have a lot of the very long-lived read transactions open on the database, because in that case, the behavior devolves into append-only behavior, and the file size just keeps on growing until those read transactions get closed. So slide 85, everyone's still there?
Yep, right here.
Okay.
Still here.
All right. Okay, so in LMDB, there's a single writer transaction, and it can be concurrent with any number of readers. So the write transactions are serialized by a single mutex. The mutex is a shared multi-process mutex, right? So it works between multiple processes. This is kind of unusual in lock design, but there you have it. Readers actually run without locks, and they can never block. There's actually the only reason a reader will not succeed is like if the hard drive has actually died. The transaction IDs are just stamped with a simple integer. It's a monotonically increasing integer. It only gets incremented for a write transaction that actually modifies data. So if you create a transaction and you commit it without actually doing any write operations, then that commit is basically ignored because nothing happened, nothing changed. And in that case, so if you end a transaction without making any changes, then the next transaction you open will reuse the transaction ID. Every transaction takes a snapshot of the currently valid meta page and then uses that for the rest of its duration. So this is what allows us to get complete isolation. You know, once you've snapshotted the meta page, it doesn't matter what other changes are made to that meta page because you don't see them. So this gives consistency and isolation in terms of ACID semantics. And just a quick review, you know, ACID stands for atomicity, consistency, isolation, and durability. So consistency means you never see a partial state, a changed state, and isolation means you never see what anybody else is doing while it's in progress. Figuring out which is the current valid meta page is pretty simple. You just look at both meta pages and you pick the one with a greater transaction ID. Now this is a little bit special. You have to make sure that all of the data structures on these pages are aligned with the hardware. So these data pages are page aligned to work with a memory manager, and the actual ID integer is CPU cache aligned. And since it is a single machine word, we can read it and update it atomically without using any particular special operations. This is how we get atomicity for ACID transactions. updating the transaction ID as a single atomic operation. During a commit, so this goes back to your question of how do you actually write to the database if the memory map is read-only? Well, we actually use regular write system calls to write to the database, right? And so then, and these writes are only performed when you actually call transaction commit. At that point, we do the series of writes, and then we do an fsync to flush all of the data pages out to disk. And once that fsync completes, then we update the meta page, and that particular meta page update is a synchronous write operation, and it is atomic. So we know that when that write operation completes and returns without an error, we know that the entire transaction has been written successfully. And this is how we get durability guarantees. Now, if the system crashes before this meta page update completes, then everything written up to that point is just ignored, and the previous meta page remains valid. Now, slide 89, read transactions do things a little bit differently. At the very beginning of a read, or the first time you try to perform a read transaction in any particular thread, the reader has to acquire a slot in a readers table, which is just an array of process and thread IDs and transaction IDs. This is also a shared memory data structure, but it's separate from the memory map that the database lives in. Again, all of the elements in this array are CPU cache aligned so that they can be accessed atomically without interference from other CPUs or threads. And once a particular thread acquires a slot in this table, that slot ID is stored in thread local storage. So any other read operations that the same thread performs can just operate immediately without further reference to the lock table. So this is how we get lockless read behavior. The very first read acquires a lock momentarily, but every read after that can run with 0 locks. As I mentioned before, we prefer to use old pages from the free list before trying to allocate new pages from the OS. This is slide number 90. The free list is sorted in numerical order, and we just pull pages off the list from beginning to end, oldest first. Now, in order to do this, we have to know which readers are still referencing particular transactions. Any transaction that we see being referenced in the readers table puts a limit on how much we can reuse in the old pages. Now, the interesting thing about this is the writer doesn't need to lock the reader table when it's scanning for readers. So readers never block write operations. And there is a consequence of not taking a lock here, which means that the writer might not necessarily see up-to-date information. But that actually isn't a problem for us because we don't need to see the newest reader info. We only need to know who's the oldest reader and avoid stomping on the oldest reader. So this all works out. Slide number 91, little details that, if you were taking a computer science course and looking at B trees, they're all lovely and pristine and they work so perfectly in the textbook, but in the real world, things are a little bit different. In the textbook examples, they always assume that every record in your data structure is the same size. And for example, in OpenLDAP, records are highly variable in size. In textbook examples, They show you using pointers to get from one page to its parent or from one point to its sibling. And in a copy on write database, you can't actually do these things. It doesn't work out. For example, on slide number 92, when you assume that all of your records are the same size and you want to put a new record in a page that's already full, it's very simple what you do. You just slice the page in half and create 2 new pages. That's slide 92, 93. Okay, so we slice the page in half, we create 2 new pages out of it, and then we can put our new record in wherever we want, either in either of the 2 new pages. So on slide 94, we put our new record in. Great, no problem. Now, in reality, when we've got records that are all different sizes, like on slide number 95, the question of where do you actually split the page becomes more interesting. I'm pointing this out because this turned into one of the more difficult pieces of code to get correct in the early versions of LMDB. We had a lot of problems with that. So where do you split the page? And the answer is, it depends. There's no quick way to do this, to decide. So when we have a page with a small number of records, we just count, tally up the sizes of every node up to the point where we think the new record belongs, and we just split as soon as we find a place that fits. For pages with a lot of records, and small number and large number of records here are both total guesses that we just looked at from observing usage patterns. For pages with more records, we assume that they're all small enough and that just dividing the number of records by 2 will give us enough space. And so far, that's worked out. So in a typical B plus tree, as again, a textbook example, you've got pointers everywhere. So the root node points to all its children, and the children point to its parent, and children point to each other. But that doesn't work in a copy on write tree because a particular data node actually has multiple parents, and a particular data node probably has multiple siblings too. So you don't know which parent to point at, and you don't know which sibling to point at. So these pointers, which are used to optimize traversing the tree in a typical B tree, can't be used here. If you look at typical B tree implementations, they will dynamically allocate memory to store the pointers between each node. And doing this is extremely messy because of the extensive malloc-free activity that we've already seen causes heap fragmentation. And it has bookkeeping costs as well. In LMDB, we actually use a fixed-sized cursor stack to record our tree positions. And since it's fixed size, we don't need to do any dynamic allocation. Slide 100. How many of you guys have ever run across the quicksort algorithm?
I think all of us.
Okay. Have you ever read the source code for it?
Yep.
Okay. So this was an example from a textbook that I found. It seems to be quoted all over the place. And the thing that's interesting to point out here is they set their stack size with a maximum of 50. And nobody ever explains how that number 50 was chosen. Why did they set max to 50? And why do they know that 50 is big enough? Right. And it turns out that the depth of this stack is can never exceed, you know, the logged base 2 of the number of nodes in a tree. So if you actually have a 32-bit machine or a limit of 2 to the 32nd nodes, elements in your tree, in reality, you only need up to 32 slots in your stack. And so whoever wrote this example and chose this number 50 wasn't actually thinking about what's the max size he actually needed. Okay. Other niggling details inside LMDB. When you have multiple cursors open at the same time in the same transaction, changes made by one may affect all the others. So, for example, if you have two cursors pointing to the same record and you use one of those cursors to delete the record, what happens to the other cursor? In databases like Berkeley DB and SQLite, well, in Berkeley DB, deleting a record just leaves a tombstone there. So it just sets a flag on the record that says, hey, I've been deleted. In SQLite, the second cursor will become invalidated. It says, hey, you don't point to anything anymore, and you have to reseek to whatever the heck you wanted to do. In LMDB, we actually track all of these cursors and make sure that when you update one, all of the other cursors move correspondingly. And so they always point to valid data. So on slide 103, I'm not sure we want to get into this, but the actual free space DB is a second B tree, and the tricky part about this is it's keeping track of our free pages, and we sometimes need to use free pages in order to update it. So it becomes a heavily recursive update. And this was something that was pretty challenging in the early days of LMDB as well. But we've gotten past that. Okay, so slide 104, special features. One of the cool things that LMDB lets you do is do zero copy writes. So you can perform a operation and request that LMDB reserves a buffer for you of a particular size, and it will return a pointer to this for you. And then you can generate your data directly into that buffer, and that means the data is entered into the database directly instead of going through a second buffer copy. This is pretty handy if you generate data dynamically. You know, if you're just saying, here's a record that's a static object and we're copying it from one point to the other point, then this doesn't save you much time. I mentioned earlier about mapping to a fixed memory address so that you can store live pointer-based objects. One of the other features that we adopted from Berkeley DB here on slide 106 is the use of sub-databases, where we can store multiple independent B trees inside a single database environment. So, you know, in OpenLDAP, we have our main database and we have all of our index databases, and all of those live in a single file. The advantage here is that that means you can have transactions that span every single table. You know, so if you want to store a new record and you maintain 20 or 30 different indices on it, they all get updated atomically in a single operation, and everything stays consistent. Another feature we inherited from Berkeley DB is called sorted duplicates, which basically means a single key is allowed to have multiple different values, and we maintain them in sorted order. And you can specify your own sorting function to determine the order that you want to use. And there's also another option in addition to this. When you know that all of your data values are of a uniform size, we can store them completely contiguously with no extra overhead. So this is a pretty big space and performance savings for simple tables that all use constant size records. Another cool operation that we have, you can take a hot backup of the database without stopping the operation, and the entire backup is performed as a single atomic operation. And the implementation of this is probably one of the simplest things you'll ever see. It's we do a single write operation to the output file, starting at the beginning of the memory map, running to the size of the memory map. And that means we don't do any buffer copies of our own. It's just a pure DMA operation inside the kernel. Okay, so results in actual use. We found LMDB has been adopted by pretty much all of the Linux distros, all the BSD distros. It's being used on Android. It's being used on iOS, Mac OS, and our performance impact on OpenLDAP has been pretty dramatic. We've gotten 20 times faster read performance than our Berkeley DB code, and I have to point out that OpenLDAP with Berkeley DB was already the world's fastest LDAP server. Has been since 2003 or 2004. And now we're pushing even faster beyond that. And not only that, we get all this performance while using a quarter as much RAM as Berkeley did. If you've ever used Memcached, people sometimes think, a database is slower than a pure in-memory data structure. And the reality is that's not true, or at least in the case of LMDB, that's not true, because if you're not careful about how you write your in-memory data structure, and you have to use locks, then those locks will slow you down. And LMDB reads that use no locks can run much faster, even than a pure memory piece of code. So here on slide 110, this shows the time to load a database, an in-memory database with 100 million records using 16-byte keys and 100-byte values. And there's 3 different time values being recorded for each database. One is the wall clock time, that's the blue line. The orange line is user CPU time, and the yellow line is system CPU time. So how much time you spend in user application code and how much time do you spend in system calls. And you can see the difference here from LMDB to all the other ones is, again, pretty stark. While some of these databases, or like Berkeley DB, takes nearly an hour to load this data set, LMDB does it in like a second. Slide 111. This shows a single writer thread running while a bunch of readers are running concurrently. So the number of readers is increased from 1, 2, 4, 8, 16, 32, all the way up to 64 read threads. And the writer is writing as fast as it possibly can at the same time. So you can see when there's only one reader thread, LMDB can get nearly 80,000 writes per second. And as the number of readers increases, well, the write throughput decreases. I mean, that's just the way it goes. The system bus is getting burdened down. But you can compare this to all of these other database engines and see how they perform. At the same time, so while that writer is running, this is the throughput that we get on the reads. And you can see that, first of all, LMDB is getting the greatest throughput, but the other interesting thing on this graph is that RocksDB is getting pretty good read throughput as well. Now, the tricky part about this is that there's actually 2 sets of results for RocksDB on this graph. There's RocksDB and there's RocksDB PFX. So the RocksDB graph by itself, that's the performance you get out of the box with the default settings. And with PFX, that's the performance you get with a highly tuned setting where I had to actually configure 42 different parameters to actually get it to run this fast. It's not a task for mere mortals. It requires hundreds and hundreds of runs to validate your choice of settings to finally say, yeah, this is a good set of settings. So the point here is to show that it's possible for these other guys to get pretty good performance, but the investment of effort to get there is pretty intense. Okay, on slide 113, this is a similar result as the previous graph. We're loading a database that is 160 gigabytes on disk inside a virtual machine with only 32 gigs of RAM. So we're looking at a database that's 5 times larger than RAM. And again, this just tells you the time it takes to load the database. Again, with Berkeley DB, we're looking at nearly 3.5, 4 hours. The other thing that shows up from graphs like this is where the user CPU time is actually greater than the wall clock time. And that tells you that the database engine is using multiple background threads to try and get its work done. And you'll see that in LevelDB and Basho and RocksDB and TokiDB and WiredTiger LSM. So all of these database engines rely on having excess CPU power to get their work done. They assume that a background thread can get work done while the application is running. But that means, they're assuming that they can eat up your CPU that you thought your application is going to be using. So again, like the previous test, here we're showing how write performance scales while the number of readers is being increased. And in this case, you can see that LMDB write speeds are pretty horrible. And all of the other LSM-based engines have very good write performance through all of these tests. And that's generally what you expect. The log structured merge trees are write optimized designs. They're supposed to have very good write performance. And here you can see that they are delivering that. But at the same time, their read performance really isn't all that great. And in the design of LMDB, our focus was on read performance because that's the heaviest task for an LDAP server, and that's the heaviest task for a lot of database applications. And here you can see that on slide 115 that the read performance of LMDB, beats all of the others, even the highly tuned RocksDB. All right. Most of these other graphs tell much the same story. You can find all these graphs on the SIMUS website if you want to study them in depth. Some of these benchmarks, like here on slide 117, the database engine actually crashed. The WiredTiger LSM engine basically filled up the disk, which was not expected because the database should only have been 160 gigabytes, and it was on a 500 gig partition. But anyway, it filled up the disk, which meant that its background garbage collection thread didn't get to run fast enough to keep up with the workload that was coming in. So that's the danger you always face when your database engine requires background garbage collection. It may not succeed. Here on slide 119, we're showing memcache. And there's Berkeley DB 5.3, LMDB, memcached, and also InnoDB. This is from MySQL, I think 5.6, which has a memcache handler built in. And this shows the time in milliseconds to process read operations and write operations using a single client thread. And the various charts show the distribution in percentiles. So the average response time is the second bar from the bottom. You can see that LMDB and memcached have pretty tight time distributions. InnoDB is kind of all over the place, you know, from as fast as 0.1 milliseconds to as slow as 800 milliseconds. And Berkeley DB has that same kind of gross distribution. You can see also on this chart that memcache is slightly faster for writes than LMDB is. And again, that's kind of expected. And then things change when we throw multiple threads at the workload. Here on slide 120, using 4 threads, and this is a quad-core test machine. And in this case, LMDB is faster in all cases. And again, that's simply because you know, its reads have no overhead and its writes are fairly simple. And the locking inside memcached is actually much more complex, even though it's using a pure RAM data structure. Meanwhile, Berkeley DB and InnoDB are both, you know, still all over the place. Here's another test using the Yahoo Cloud Serving benchmark. It's a pretty standardized benchmark for networked database servers. And we're testing LMDB versus LevelDB. And again, you can see the speed, the time it takes to insert 100 million records is 5 times faster, at least, for LMDB than it is for LevelDB. And the latency is rock steady. You can see in LevelDB, the variation in latency is incredibly spiky, and it goes all the way out to you know, 28 milliseconds, whereas for LMDB, the latency is always on the order of microseconds. Here's the latency plotted out again. It's interesting that you can't actually see the 95th or 99th percentiles for LMDB because they're actually the same as the average. Whereas for LevelDB, the 99th percentile latency is out there at 10 or 20 milliseconds. And here in 123, this is that same 100 million record database doing a read-write workload where it's 20% writes and 80% reads. And just the time it takes to do 1 million operations. So the chart shows throughput as well as the latency for writes and the latency for reads. And again, you can just see that the throughput for LMDB is always fairly steady, the latencies are fairly steady, and for LevelDB, they're all very spiky and twice as slow. Let's see, did you guys have been looking at cryptocurrencies?
Yeah, a little bit. I like this quote from the CEO.
Yeah. So Armory is a company that puts out a Bitcoin wallet, and yeah, they had some pretty great response after they switched from LevelDB to LMDB. Load time from 3 days to less than 2 hours. Okay. Some more LDAP results, more specific to OpenLDAP. you can see on there's 4 different tests here. One is a pure search test. One is the search rate with write operations mixed in, and one is a pure modify test, and the other one is the modify rate mixed with search operations. And you can see that OpenLDAP on the far left is OpenLDAP 2.5, and the next column is OpenLDAP 2.4. Others, number 1, 2, 3, and 4, are proprietary LDAP servers that we're not allowed to name. So one of them there has a very good search performance when there's no other activity, when there's no other write activity. But as soon as you throw write operations into the mix, then all of its performance drops. So you're looking at a database where writers and readers block each other. And you can see 389DS, Active Directory, and Apache DS. So this is the landscape of LDAP servers these days. And as I mentioned before, you can find multiple pages of benchmark reports on the Cymus website. All of these software packages are available from Cymus. We've got LMDB support for not just for OpenLDAP, but also for Cyrus Sazzle, Heimdall Kerberos. Lots of other open source projects have adopted it. Coming down to the end, when I wrote LMDB, I didn't really have any idea of how well it was going to work. I mean, we really didn't even know if it was going to work. And over the past few years, we found that it's turned out to be extremely powerful, extremely effective. And it's just been a huge win for OpenLDAP and for other projects too. There are some other things that we've been playing with for LMDB 1.0. And the basic design is still the same, but yeah, there are little things to tweak here and there. And here we are.
Wow.
I have a question.
We got questions. Hold on.
Okay.
Here's Shay.
There was a mention earlier about a cursor, and I'm not familiar with that term. What does that mean?
Okay. A cursor is, you can think of it as an index pointer that keeps track of your position in the database if you're iterating through it.
Right.
Does that help? Right.
Yeah. Yep, that's good. Earlier this month, you tweeted about fsync and Linux being a hot mess, and that you knew this when you were coding LMDB, and you worked around it. How did that work out?
Okay, so if you were following along, the Postgres guys discovered they had a problem, which was when the database commits a transaction and wants to be durable, you got to do an fsync call, all right? And it turns out that if an fsync fails, okay, a subsequent fsync won't remember that there was a failure, all right? Now, in the case of Postgres, when they do an fsync and they get a failure, they come back later and try again, okay? In LMDB, if we do an fsync and we get a failure, we immediately return an error and stop, okay? So that's the first thing, is we don't do a retry on a failed sync. And the second thing is that when we actually update our meta page, that is using a single synchronous write operation. So that write operation either succeeds or fails immediately on its own, and it doesn't depend on a previous error status being true or false. All right. So the problem that Postgres ran into was, one, they will retry after an fsync, and two, they will believe after the second fsync succeeds, they'll believe that everything succeeded. But in reality, in reality, if the previous fsync failed, everything that failed with that is still failed and missing. And so they would wind up with a corrupted database because they believed that because the second fsync succeeded, they believed that everything succeeded.
Okay.
Okay.
So tell me, what does the LMDB do after a failure from fsync?
There's two things, all right? One, if we actually get an fsync failure, we immediately stop. We don't do any retries, all right?
Does that mean you just drop the whole database, or what?
Well, we don't drop the database. We return a fatal error to the application, right? And then the application is going to have to ask the user, hey, what do you want to do? Because this thing's hosed, all right? And the other thing that we do is we don't do two fsyncs in a row, all right? We do one fsync to flush all the data, and we do one synchronous write to do the transaction update in the meta page. And so even if the fsync was to lose track of itself and forget that something failed, the synchronous write will succeed or fail on its own, and so it won't mask any other errors.
For those wanting to look in, that's a really good explanation of the fsync problem. Richard Hipp, who wrote SQLite, gave a talk at the SouthEast LinuxFest called The Great Fsync Bug, where he goes into just that issue in depth for almost an hour. It's on the YouTube channel. It's totally worth watching because, as you can imagine, Richard Hipp has just as intricate of a knowledge and hatred of fsync as you do.
Yeah, I'm sure. Exactly. Yes. Yeah.
And Linux people have known about this for 7 years and they haven't fixed it yet?
Yeah, isn't that great?
Oh, okay. All right.
I mean, there is an element of open source where if nobody who can fix it cares enough to fix it, then it isn't going to happen.
Okay. We'll all jump on that then.
There you go.
Any other questions?
I'm just curious what license it's under.
It's under the Open LDAP license, which is basically a BSD 3 clause.
Is the source code bundled together with Open LDAP, or are they separate?
Currently, it's both. Right? It's always bundled inside Open LDAP. We also have exported just the LMDB code itself to a repo on GitHub.
Any other questions? Okay, Howard, thank you so much for presenting LMDB. And we know it's late there in Ireland right now. We appreciate you staying up so late to present this. I hope to find some projects that I can use LMDB on.
Great. Yeah, I didn't realize that I'd gone 90 minutes on you guys, but thanks for having me with you.
All right.
Well, thank you so much for staying up late. We really appreciate it.
Yeah, my pleasure.
Okay, we're signing off. Bye, Howard.
All right. Ben.
Yes, Jeremy.
Is Jim Salter still there?
Yes, he is.
Whenever you kill the stream, I want to talk to Jim.
Okay. All right. I'll kill the YouTube stream. Okay.
Jim, while you're so convenient to me, I have to ask you the obligatory transcendental angst question of, would you prefer to be an attendee or prefer to have a really cheap expo?
Attendee, probably. I appreciate the offer.
Yeah, well, I know you struggle with it because, well, having been to some of the other events, you know of the value. Like, a lot of people don't understand like how really cheap the expo hall is itself.
Well, I really do. I don't really have the personal bandwidth right now to dump into it. It's a lot of work on my end. It's a great value. I am right now too lazy to do it.
Fair enough. I figured I would check.
Yeah, I'm going to be selfish and actually attend the damn event rather than working my way through it. Which is also a testament to the value of self. So, you know, you're coming out aces either way here.
Yeah. While you were so convenient, it saves me sending an email, and God knows I've done enough of that in the last few hours. In fact, probably everyone on this call got an email from me in the last few hours.
I have already rolled.
Thanks for putting it together, Ben. He was a really good talker.
Yeah, he's good.
Yeah.
And Jeremy, I'll probably come with a backup presentation if you got somebody that quits on you.
Oh, absolutely. Yeah. There's always last minute, weird flight things. The disaster scenario I could have right now is Colin Charles is on a very tight turnaround on his flight schedule, and he's given 3 talks like bam, 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 all in the same day. So if he has flight chaos, that could leave a gap.
All right. Okay. Oh, we can't wait for self, so that'll be fun.
Let me put a quick announcement. Anyone that's going to be coming to UC Lug, we're going to start meeting at the Brickyard makerspace. They're going to be opening up here soon, or I think they just opened, and we'll be moving there now. So
awesome.
Otherwise, y'all have a great night.
All right, you too. Bye, all.